Hey everybody, Mrs. KJ here. We're going over 2.07 molality and mass percent. So before we did molarity, and if you notice, there's just the difference of this L to make it molality, but there are many differences to follow. All right, so concentration expressed as volume ratios, concentration can be expressed as mass ratios, and concentration can be expressed as molality, which is moles per kilogram. The concentration of a solution can be described in several ways. If a liquid solute is dissolved in a liquid solvent, for example, then a volume percent might best describe the solution. A solid solute, such as salt, dissolved in a liquid solvent like water, meanwhile, would ideally be described in terms of mass volume percent. But if the mass of the solvent is of interest, then the calculation that should be performed to describe the concentration is moles per kilogram, and that's called molality. Goals for the lesson: describe two ways of expressing percent concentration of a solution, so volume, and mass. Define molality, or molal concentration. Calculate the molality of a solution. And on slide 2, you can go ahead and get the study guide. And from the study guide, I just put our first paragraph in that we read and our goals. And the key word is molality, the concentration of a solution based on moles of solute per kilogram of solvent. Review the concepts of molarity and mole fraction. So molarity is a measure of the number of moles of a solute per liter of solution. Molarity, moles per liter, or capital M italicized, is probably the most common way to talk about the concentration of a solution. In some cases, it is more useful to talk about the concentration in terms of mole fraction. Mole fraction can be discussed in terms of either the solute or solvent with respect to the entire solution. Either the number of moles of solute or the number of moles of solvent is divided by the total number of moles in a solution. And so again, they put mole fraction over here. So it's either moles of solute divided by total moles of solution, or again, you can do the solvent divided by total moles of solution. And concentration can be expressed in molarity and mole fraction. And so I added molarity and mole fraction into our keywords and pronunciation. Even though they were from a previous lesson, it's good to have them all in one place. Concentration can be described as a percent. So let's look at the picture first. We can say we have 90% water, 10% salt. We can say we have 3% salt or 97% water. Molarity and mole fraction are not the only ways to describe the concentration of a solution. A glance in a medicine cabinet or kitchen pantry gives us an example of an alternative. Isopropyl alcohol, used to treat and clean minor cuts and scrapes, may be 91% alcohol. That is, it contains 91 milliliters of isopropyl alcohol mixed with 9 milliliters of water to make a 100 milliliter solution. This 91% is called the percent solution. Likewise, labels on fruit juice containers often state the amount of juice that is actually in the drink by using percent solution. A label might say, "now with 25% real juice." This statement means that 25 milliliters of real juice is in a solution that contains enough water to make a total of 100 milliliter solution. All right, so let's add in percent. And we'll put that under our key words too, because it is another way to talk about concentration. And again, the key thing is that we have a total of 100 milliliters. So you have to add them up, 9 milliliters of the first liquid, 91 milliliters of the first liquid and 9 milliliters of the second liquid to get you your total of 100 milliliters. Once you have a total of 100, you can easily make them into percentages. Volume solutions are made from a liquid solute and a liquid solvent. So both the alcohol and the water were liquids, even though they were divided into each other to have a mixture. Percent solutions are often called volume calculations. The generalized formula for this calculation is as follows. Percent of solute equals the volume of the solute divided by the volume of the solution times 100%. So in other words, if I have 10 milliliters of isopropyl alcohol, the total bottle has 100 milliliters, you just divide it times by 100 and you get 10%. We could also do this with volume of the solute with fruit juice, 18 milliliters of fruit juice. The total container holds 100 milliliters and therefore it's 18%. So divide and then multiply by 100. So we will just add this into our notes under our percent of solution, and now we have percent of solute. The concentration of a solution can also be given in terms of a mass-mass ratio. Suppose your solution contains a solid solute. In this case, you would not use a volume-volume percent as you do with liquids. Instead, you might use a mass-mass percent. Here's the formula for calculating a mass-mass percent. Percent of the solute equals mass of the solute divided by mass of the solution, again, times 100. Notice that in this case, as in the case of the volume-volume calculation, you are concerned only with the solute and the solution as a whole. Okay, so we have the mass of salt and the mass of solution. So the mass of the salt is 5 grams. That means the mass of the water is how much? The mass of the water would be 95 grams if the entire solution is 100 grams. So if I want the percent of the solute, 5 divided by 100 times 100 gives you 5%. Here's another example. Again, it's mass over mass. So the mass of the salt is 2 grams. The mass of the solution is 100 grams, which means I have 2% solute or 2% salt. What percent water would I have? 98%, because when you add it up, it's got to equal 100. So I added to our volume one that you use that when they're both liquids. We can also do percent of solid as a mass over mass of solution, and we use that for a solid solute. Look at a problem in which the concentration is calculated in mass-mass percent. Dextrose is a simple sugar that dissolves easily in water and is used by both plants and animals for energy. And here's an example of dextrose crystals. A laboratory technician is asked to make up a 3,000 gram of solution in which the sugar dextrose is mixed with water. The final concentration of dextrose is to be 5%. How much dextrose does the technician add? Okay, so first of all, always write down what you're given. So we know the solvent is 3,000 grams. Okay, I copy-pasted the problem into the notes because there was a typo. So let's look at this again. So you're given the solution is 3,000 grams. So it says that you have a 3,000 gram solution, okay? And then the final percent of dextrose in the solution is your 5%. So we want to use the mass of the solute divided by the mass of solution times 100%. So that tells us that we need to see how much we have. So if we take X grams of dextrose divided by the 3,000 grams of solution, that's going to equal 5%. So remember in math class, you have to change 5% into a decimal. You do that by dividing by 100 or moving the decimal place 2 places to the left. So 5% becomes 0.05, and that equals X over 3,000. Or if you like having X on the left-hand side of your equation, it's the exact same thing, but X over 3,000 equals 0.05. Then we multiply both sides by 3,000 to get X equals 0.05 times 3,000 grams. And that calculation shows us that there are 150 grams of dextrose. And so if we wanted to double check our math, we would say 150 grams divided by 3,000 grams equals what? Well, it equals 0.05. So we times that by 100, which gives us our 5% solution. And I just quickly added in here that the percent of the solute equals mass of solute divided by mass of solution, because sometimes when you read things later, if you don't have everything written down, you might forget, oh yeah, what did that equal? What was that from? So that is our total equation for that one. All right. The concentration of a solution can also be expressed in terms of molality. Chemists often calculate concentration in terms of moles of solute and grams of solvent. So like moles of salt, grams of water. Molality, with the symbol M lowercase italicized, is a measure of the number of moles of a solute in 1 kilogram of solvent. It expresses the concentration in terms of the mass of the solvent. Be careful though, the word molarity, capital M, sounds similar to molality, but molarity is a measure of moles per liter. Molality, little m, is moles per kilogram. For example, a 4.0 molal, or 4.0 little m italicized, solution contains 4.0 moles of solute for every kilogram of solvent. On the other hand, 4.0 molar, or 4.0 capital M italicized solution contains 4.0 moles of solute for every liter of solution. So that's the big difference. They show it over here. Again, we have moles of solute, in this case salt, divided by kilograms of solution or water. That gives us our molality. We could also say, all right, what if we have 6 moles of solute divided by the 1 kilogram of water, and our molality this time is 6.0 molal, or 6.0 lowercase m italicized. It has to be italicized because if you just leave it as a regular m, then it means meters. So that's why they have to be italicized. So I added to our notes, molality, lowercase m italicized, equals the number of moles of solute in 1 kilogram of solvent. It expresses the concentration in terms of the mass of the solvent. For example, a 4.0 molal solution contains 4 moles of solute for every kilogram of solvent. On the other hand, a 4.0 molar, 4.0 capital M, solution contains 4.0 moles of solute for every liter of solution. And again, your M needs to be italicized. So those are the big difference. Molal is kilogram of solvent. Molar is liter of solution. Okay, so molar, liter of solution. The meaning of M. The lowercase italicized m is the standard notation for mass and for molality. A lowercase non-italic m stands for meters. You can tell what the small m stands for based on the context. Molality is used to describe the concentration of solutions. Mass is used for weights or amounts, and meters are used to describe lengths or distances. Calculate the molality of a solution. Step through this molality calculation to see how to figure the molality of a solution made up of 40 kilograms of Br2 in 4 kilograms of water. And I'm going to run out of time, so we will start right here in our next video.